Okay, so this is going to be part 3. I'm just going to continue the work from part 2, in which that I basically am solving for the information for this resistor. So I ended off kind of solving out first the resistance equivalence of the circuit by calling this a series and squishing it down to the 7. These are in parallel, so that reduces, remember this reduces to 2.5, and this adds together to 11.5. Like that, and that's a resistance equivalent. So now basically I'm going to work backwards through these 3 diagrams to get back to the 5. So let's start off here. I could find the current of this system as V over R, where I could use V, this is just Ohm's law in the most simple case, like this, which is kind of nice. So 12 divided by 11.5, I get a current of 1.05 amps. Okay, so that's the current there. Now, from here to here, our step was that we are in series. So, I'll go in green just to show you the differences, right? So, series means that the current must be the same for all of these. So, that means I is going to equal what we just found. 1.0, well, actually it's 0.4. We'll just go with 0.5, that's fine. 0.5 like this. Which means each of these, I, is equal to 1.05. 1.05. 1.05, there we go. This is I for each location. Now I need this because remember I have to go back to this. So I need to figure out more or less the winning one. I'll put it in yellow because I don't want to be too distracting. Is I need to figure out this guy right here. Because that one has the 5. This and this is not relevant to the problem, although we technically could find everything. So I'm just going to focus on this middle resistor because I kind of want to branch it back out to the 5. So with that said, I have current, I have resistance, I can solve for voltage, which is important. So I'm going to solve for voltage of the 2.5 ohm resistor by finding I times R. So the I there is what we're using from previously, and then R at that point is the 2.5. So 1.05 times 2.5 gives me a voltage at that location of 2.6, let's round 3 volts. Okay. So remember, this one was originally a parallel, which means the parallel has the same voltage. Which means the voltage here, which I just calculated 2.63 volts, is the same for both of these, 2.63 volts. 2.63 volts. Now once again, I want this part of our circuit. Although I could find information, I'm going to ignore it. I just want to find this information because this is irrelevant to the problem once the 5 ohm resistor. So with that said, I have these 2 pieces of information. I have voltage and resistance, which means I can find the current. So the current through that section with the same voltage, the 2.63 volts divided by the 7 ohm resistance, give me a current, 2.63 divided by 7, 0.3, I'm going to round it to 8 amps at that location. Very cool. There we go. So now I look back and see what this was originally. This was originally a series right here, which means series equals the same current. Which means this current is the same right here. Now I'm going to ignore the 2 because it just asked for the 5. And this is the resistance. And if you notice, lo and behold, we can find the voltage. The voltage is going to equal to IR there, which will be 0.38 amps times 5 ohms. 0.3 amps times 5 ohms gives us our answer of 1.9 volts. So we solved the problem. Now the problem says what's the current or voltage drop at this location. So officially, I'll write the answer in red right here. The answer to this problem is the 5 ohm resistor experiences a 1.9 volt drop right there and has a current of 0.3 amps. And there we have it. So, there we go. Notice that, I ignored all the other stuff because it wasn't really focusing on anything else. We just wanted to focus on this. So numerically, how did we do this? This is more or less step 1. Break this one down. Step 2. Break these two down. Step 3. Break this down. This was step 4. Was this circuit. Step 5 was finding this. Step 6 was finding this. Step 7. And this was step 8. So it's a little, that's why I decided to number this, because I kind of did it in, in an interesting order. So this key right here equals, let's do that, go back, equals order solved. To that. All right, let's do one more. So let's go back to this. So what was the voltage difference? 1.9 right here. Okay. Solve for R. Oh goody. Well, this one's a little different because what you could see here is now we have a variable in our problem. So this one's more like a resistance equivalence type of problem versus the one we just solved. So it's slightly different, but why not? Let's see something new and different. So let's solve for R. So we have a 2, 5, 3, and a 5 and a 3. So I'm going to draw this out. So at the top I have a 2, 5, 3. And then I have a 3 and a 5. Is that correct? Let's go back. Oops, I guess I have to go back here. 5 and a 3, right? And then I have an 8 and a 9. So 5, 3. This is in series with this 8. We have this. We have a 9. And we have another one right here, I believe. I'm just going to verify this with the drawing. 2, 9. This is 12. That's the 8. Okay. Looks like we're good. This is 12. So this is more or less a resistance equivalence problem where we have a variable. So let's solve it out. So I'm basically going to keep going, and then as soon as I get to the R, I'm just going to leave it as R, and then write an expression to solve it. So this is what it looks like. So notice I'm going to start right here because this is series and this is series. So I'm actually going to do a nice double, reduction. So 2 plus 5 plus 3. So 2 plus 5 is 7. 3, this makes this 10. 5 and 3 makes 8, so this is in parallel right here. This is our 8. This is that's 9. Sometimes I do this too where I forget to put the resistor back in, so I might just, write it like that. So this is sloppy, so pardon my sloppiness with that. So from here to here is a parallel. Again, I can't do this yet because I have to get rid of this because these are in series. So that's a parallel. So what does that become? 10 inverse plus 8 inverse inverse. So now what I have is this still unknown R. this reduces to 4.4. Again, I'm dropping all the units out just for speed. I have a 9 here, and then a 9 here. And of course this is 12. This was 12. So remember for here, what I did is 1 over 10 plus 1 over 10 equals 1 over REQ to get to the 4.4 right here. And those are both 4s. 4.4. Well, at this point, now I have everything in series. So if I were to add them up, it would be 9 plus R plus 4.4 plus 8 equals resistive equivalence, right? At this point would be our total. So we're almost done here because we really can't solve it anymore. If you notice, we could kind of reduce this down. So 8 plus 4.4 plus 9. R plus 21.4 equals REQ. And quite technically, that is all we know. We can't solve this. If we were given the current around here, sure, we can solve for it. What we have is, you know, even if we try to write current is V over REQ. So, but we don't know what the current is. So this would just be 12 volts divided by REQ, which would be R plus 21.4 ohms, more or less. So, unless we're given any more information, this is pretty much it, which they might have you do on the AP, is just have you, relate things in terms of variables. If they did give you a current and just throwing one out there, say well, it was 1 amp, then we could solve this problem. So if we knew the current in the battery was 1 amp, of course I'm making this up, it's not in the problem. The way we would solve it would look like this. We have 1 amp is equal to 12 over R plus 21.4. So I would solve this by multiplying this whole thing up to here, which would become R plus 21.4 equals 12. Now notice it was times 1, so that's why it's left like this, which makes it 21.4 minus 12. I'm sorry, 12 minus 21.4. R would have to be negative 0.4 for it to work, which basically means that this number, actually I should do this. Well, this is good to see. There's no such thing as negative resistance, so this would not exist, or in other words, amperage of 1 would not work for this problem. You'll notice that I just chose this number. So anyway, that's how you would solve it. You could always check your work by saying, is my resistance positive? It should be. This amperage would have to be way higher for this to work. It would have to be a negative resistance. So anyway, the main point is these are how you would solve such a problem like this. Is if you have your resistance equivalents, you reduce it down, and then if you had a current through the battery. So basically, if we had this scenario, if we had 12, where this is REQ, and the problem says, oh, well, the current through the battery is given. Which is not. So, there are a few types of problems. Definitely try them out. Your homeworks are very similar to these. If you have any questions over the break, you can absolutely email me, and I could probably do a video showing you how to solve some of these. So best of luck, and have a nice break.